Hello there. Let's do an introduction to networking. Now, when it comes to networking in A+, obviously we're going to go up to a certain point, after which then it's more for Network Plus to handle further concepts. But we are going to go through a couple of videos for networking in A+, both in Core 1 and a smidgen of references in Core 2. Obviously, networking in modern IT is pretty inseparable from other technologies like your operating system and your security. So let's get into it and start defining some network types. We generally categorize our networks in a couple of interesting ways. First of which is local area network, or a LAN. Now, local area networks are generally a small scale network. We're talking about room-sized, building-sized networks. Now, besides being building-sized, they are also considered to be quite fast. If you go around saying your LAN is running at about 1 gigabit per second, that isn't very impressive or surprising nowadays. That kind of speed is pretty normal for LANs. Now, keep that speed in mind though when we move on to other kinds of network types. Another characteristic of LANs is they're generally private. Either you or your employer owns everything to do with the LAN. It's your devices, it's your cables, it's your configuration, it is all yours. So you can be pretty confident that you and at most your guests and customers are the only people on that network. Compare that to the exact opposite, which is a wide area network, or a WAN. Now, with WANs, they are generally large scale. We're talking intercity, intercontinental kind of distances here. And yes, the internet is technically the world's largest WAN, made up of a variety of ISPs and IXPs. Now, generally when we're looking at speed compared to a LAN, your WANs are generally slow to moderate speed. Although you do get some pretty impressive speeds nowadays for the internet, it's a lot easier and cheaper to get your LAN to go faster than to get a faster WAN link. And your WANs are generally not that private. You do have some options to have a more privatized connection than what you get with an ordinary internet connection, but at some point, every customer of a WAN provider is going to be sharing that infrastructure with other customers. Now, those are our two extremes for network types, but we also have a couple of others that'll pop up as well, like a personal area network, which will usually be abbreviated to PAN. Now, these are very small scale, usually serving only 1 or 2 people, and often make use of short-range wireless technology like Bluetooth. Now, in terms of any other kinds of network types you come across, there are others, but usually you can figure out from the name the characteristics about it now that you know about LANs and WANs. Another kind of categorization we have for our networks is what it serves or who it serves. So in this case, we've got small office, home office, which is usually used to describe a small-scale network. And it's obviously, as the name implies, meant for a home network or a small business. And usually the SOHO network is built around the wireless router that you have in that network. In fact, for a lot of people, that is the only network appliance in their home network or their small business network. But in fairness to this Wi-Fi router, it is a combination appliance. It bundles together an actual proper router that makes a decision about where to forward traffic based on source and destination IP addresses. It has a wireless access point. It has a switch. Usually those RJ45 connectors on the back there that you plug your Ethernet cables into are actually switch ports. It usually also has a DHCP server built in so that the average home user who is not technically inclined can just cable up or connect to the Wi-Fi, and the IP address information is automatically assigned to them. Don't worry, we are going to be talking about DHCP and all of that in later videos. And then depending on where you are in the world, there might be a modem built in, although that is optional. In some parts of the world, the router will have a modem built in to convert the Ethernet signals to whatever signaling technology is used by the service provider. Otherwise, your modem is usually an external appliance, often installed on your premises by the ISP, and you cable up to it. And then a coffee maker, but I'm still waiting on this feature to be included in my home router. Now, SOHO networks, or as they're abbreviated to, can be expanded upon. you are not limited to just that one appliance. You can usually get your hands on consumer or SOHO switches, wireless access points, etc. to make the network a bit larger and a bit more capable of supporting more devices, or at the very least improving its wireless coverage. But these small office, home office, consumer appliances are not ideal for larger and more demanding applications, which is why we get enterprise networks as another type of category. Usually your enterprise networks are larger scale and used in the workplace, and often make use of enterprise-grade appliances. This is what your enterprise appliances may look like. Believe it or not, that is an enterprise router, and that is an enterprise switch. The form factors aren't exactly exciting, but they are 19 inches wide, usually, and are able to fit in a standard server rack or network cabinet. So usually you get a lot of extra features out of these devices, stuff that you would never ever see in a SOHO appliance. Also, greater capacity to handle larger volumes of traffic, and of course, you pay more for this pleasure, or your boss does. And the design focus for these appliances is usually to have better availability and security than SOHO appliances would. Usually these devices are designed to be a lot more reliable, a lot more robust, and to have options to improve network security. Not to say your home network isn't secure, but there's just going to be simply technologies not present in the home network that would be useful in the workplace. Usually an enterprise network will include dedicated appliances. Routers are routers, switches are switches, wireless access points are just wireless access points. And you'll also get appliance types that you will not usually find in a SOHO network, like dedicated firewalls, intrusion detection and intrusion prevention systems, wireless LAN controllers, and loads more. And then we also get data center networks. This is a type of enterprise network where you usually find servers and various kinds of data storage solutions, but generally no users will be present here. Data centers might look something like this, or maybe not as shiny and clean and technologically interesting, but they definitely will be server racks and loads of equipment and loads of cabling. And oftentimes a different class of enterprise appliances get used. A lot of the enterprise network vendors usually have routers and switches that they design with the intent of being used in a data center network. Although they could be used in an enterprise network where users are present, they're going to have some features that just make them a little bit better at dealing with server traffic. And some different design paradigms will be used when doing a data center network. Although at A+ level, you don't have to stress too badly about that. You'll start worrying about the approach to data center network design when you are looking at the appropriate courses in your future. But as you can imagine, considering this is where a lot of the processing and storage for valuable enterprise data and services is kept, usually security is quite high, both for cybersecurity and physical security. Now, before we get too stuck into more details about networking, I want to show you something about networking models. And the first model I want to show you is something called the OSI model, or the Open Systems Interconnect model. Now, please be aware that this is not part of the A+ exam objectives. I do, however, include it because it does make understanding how network communications work a little bit easier. Add to that as well, a lot of network professionals will refer to network appliances by the layer at which they work, and usually it's OSI layers they're talking about. So there are 7 layers to the OSI model. Working from the top down, you have application layer, presentation layer, session layer, transport layer, network layer, the data link layer, and the physical layer at the bottom. Now, to remember this, there is a little rhyme you can remember. All people seem to need data processed. It works quite well because the words are easy to remember. Application, presentation, session. But the little rhyme or mnemonic helps a lot in terms of getting the order of those words correct. But what's the point of this? Well, originally the OSI model was created to standardize how networking was done. Prior to the OSI model's creation, various technology vendors would create their own proprietary approach to networking, which meant if you went and bought any computer equipment from that vendor, it was just that vendor you could use for everything because of the proprietary networking protocols. Now we have choice and flexibility. So the way it would work is if you're going to send some data onto the network, you would begin at the application layer. Well, actually just above it. Usually the program or software or the app that you're using will call upon a networking application service. So for instance, if you were about to send an email, your email client would usually call upon the SMTP networking application to start packaging the data that you want to send as an email. Or if you were making a web request, it would be calling upon an HTTP, more than likely nowadays HTTPS application service. Once the application layer has done its job, then it would hand it down to the presentation layer. The presentations layer's job is to make sure that however the data appears on your machine, it's presented correctly on the other side. So for instance, with that email, if I used a particular font and particular text effects, that would be represented correctly on the recipient's inbox. Even if they don't have the exact font library, an appropriate font will be used, and then the corresponding text effects like bolding, underlining, and changing of color would be done. Then the session layer is used to set up, manage, maintain, and tear down a communication session between the sender and the recipient. Although considering how most network communications go nowadays, it'll probably be more of a session between the client and the server, and then another session later for server to server, and then possibly server to client. Nonetheless though, the session layer is set up so that all data transmissions that make up this particular networking request or response will go through and be identified as being part of one communication session. This is amazingly useful, as it's the reason why you can do multiple things at the same time with networking. You can have this video open right now in one of your tabs on YouTube and be doing something completely different in another tab, and at no point do those things ever cross over by accident. And that's the session layer doing its job for you. The transport layer then gets the traffic ready to be transmitted. Its main job is to do segmentation, or to take the message and cut it up into smaller, more manageable portions that will not overwhelm the network. Then, one of several protocols can be used, the two most popular being TCP and UDP, to label and transmit the data, and try and do so reliably if it's TCP, or quickly if it's UDP. Coming down, we then have the network layer. This is where logical addressing and routing takes place. The most popular logical address is an IP address, and it's where your router makes a decision. Coming down a layer again, we are now at the data link layer. This is where we do physical addressing, which I know sounds a bit weird considering it's not the physical layer, but bear with me for a moment. The physical addressing is usually a MAC address, which we'll talk a little bit more about just now. And the data link layer's job is to make sure that the traffic gets from this device to the next device effectively and smoothly. And finally, you get the physical layer. The physical layer's job is to convert the binary data into signals that will work on the network media. Usually it'll be electrical voltages for copper cables, pulses of light for fiber optic, and then radio waves for anything wireless. Now the physical layer doesn't actually do any intelligent process, it just does signal conversion, which is why physical addressing is done one layer up where we still have a little bit of logic. Now that is if you're sending something. If you're receiving something, you would usually be receiving stuff at the physical layer, some activity on your network card, and then your network card and the rest of your computer will bring that traffic up and then pass it along to the appropriate application that you would be using to do some sort of network activity. As I said, OSI model is not part of the A+ exam objectives, but I include it because it is amazingly helpful for you to better understand networking. Plus, it also gives you a slight advantage or head start when you're going to look at doing Network Plus, because this becomes a very big deal in Network Plus. But we do have some other models to worry about besides the OSI model. We have the TCP IP model, which is something that you will see in A+, and something called the equivalent model, where we kind of merge the two together. So this is what it ends up looking like. You've got the 7 layers for the OSI model, and then for TCP IP, which is something you will find on your computer, it's a set of services and protocols. We refer to TCP IP as a protocol suite. That was developed many years ago by DARPA. It got known as DARPANET at the time and eventually evolved into the TCP IP model we use on the internet. Its top layer is called Application Process, and it is OSI aligned in that it does an application presentation and session operation. Next layer down is called Host-to-Host, which aligns directly with what the transport layer does. The next layer down is the internetwork or internetworking layer, which is obviously where we get the name internet from. And it aligns directly with layer 3 of the OSI model. And then you've got your network interface layer down at the bottom, which deals with layer 2 and layer 1. But with TCP/IP there is some confusion. If I say layer 2, for example, layer 1, layer 2, we're talking internet. But if we're talking OSI, that's layer 3. So to minimize on that confusion, what's been followed mostly nowadays is something called the equivalent TCP/IP model, where we sort of redid the naming a little bit, consolidating that to the application layer, that to transport, because honestly host-to-host aligns directly with transport of OSI, calling that network layer for clarity, and then bringing the data link and physical back in so that if I do say layer 2, we're all on the same page about exactly which layer we're talking about. Now we will revisit TCP/IP again later on in another video, but please be aware that this is what you'll see when you're prepping for your A+. This will appear in Network Plus, but it's still good to know now. So let's begin with some network hardware. So first up, you've got your NIC, or your network interface card. Now this is going to either be built into your computer's motherboard or a dedicated expansion card, like one of these two. Now generally its job is to provide physical connectivity for the computer to the network, and usually get two kinds, Ethernet and Wi-Fi. This being an Ethernet one, this being a Wi-Fi one. Now besides providing physical connectivity to send and receive the signals, it also has useful things on it like the MAC address. The MAC address, or Media Access Control Address, is a 48 binary bit address, usually written with 12 hexadecimal characters, and they look something like this. Now don't stress too badly about reading hexadecimal, we will work into that at some point in the future. But the hexadecimal numbering system is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, as you and I easily recognize that, and then the letters A, B, C, D, E, and F. What's pretty cool about the MAC address though, is it is unique to every network interface card. Assuming all network card manufacturers follow the rules, which they generally do, otherwise they face some penalties, fines, and issues, they will never produce two network cards with the exact same MAC address. This is handled by the fact that the first half of the MAC address is called the OUI, or Organizational Unique Identifier. And that part of the MAC address is issued to a networking manufacturer, whether it be for network appliances or network cards. And every OUI will be unique for every vendor. And then the second half is the vendor assigned portion, where the vendor decides how they do the numbering, and the rule is they can't produce two network cards with the exact same vendor assigned portion, which is pretty awesome. It guarantees universal uniqueness, but the reason why we don't use MAC addresses for routing, and why we use IP addresses rather, is because MAC addresses are not predictable. I cannot foresee what your MAC address is. Even if I know the make and model, I can only at most guess the OUI by looking up the OUI for that specific vendor. The vendor assigned portion, I've got no way of predicting what that would be. Then we also get patch panels and wall sockets. Now these are part of structured cabling in the workplace. So seeing these in the home network is not too likely unless you're a weirdo like me who actually does do structured cabling at home. Your patch panels and your wall sockets are passive components. They don't do anything electronically or logically. They're just providing an easier way to do your cabling in the workplace. Usually you'll find patch panels in network cabinets and server racks, and they look something like this. What will usually happen is you will bring all your network cables into either a cabinet near the users or a server rack in a networking room or a server room, and then you'll terminate the cables on the back side of these RJ45 sockets. That allows a quick and easy fly lead to be used to connect one of those sockets to an interface on a switch or a router. And generally wall sockets will be used in areas like office spaces and meeting rooms for end users to connect to, and they can look something like this. Again, the cables will usually be terminated on the back side, and then you've got an RJ45 socket to plug into there. The whole idea of this is that instead of having to run one long length of cable from like a user's desktop into a wall, into a networking cabinet, and into a switch, you run a stretch of cable from the desktop to the wall socket, another stretch of cable from the back of the wall socket to the back of a patch panel, and then a fly lead from the patch panel to the switch or the router. The benefit of doing it this way is if the cable breaks anywhere, it's usually a lot easier to replace the run from the desktop to the wall or from the patch panel to the switch, not too inconvenient. The inconvenient one will be doing the new cable through the wall, from the back of the wall socket to the back of the patch panel. But as long as you make sure you don't have rats and mice chewing through them, you should be fine. One thing I heavily encourage with this is that you do labeling and documentation. One of the most frustrating things you'll encounter in the workplace is when these wall sockets are not labeled and there's no reference in any documentation to which of these port numbers on the patch panel take you where. Usually the best idea is to put a label or sticker here on these wall sockets that indicate where the patch panel is and which port number on the patch panel this cable goes to. And then have documentation that also indicates where that port number is in the office space. Basically, on the one side, you document where the other side is. Trust me on this, it's one of the most horrible things to encounter in the workplaces when these things are not being documented. And if you are working somewhere where there is a lack of documentation on this kind of stuff, maybe suggest that you would like to track and trace these cables using the appropriate tools that we'll discuss in a later video. And then we get our switches. Now, depending on whether we're looking at a switch in the real world or a network topology diagram, that's what they look like. In topology diagrams, generally switches will be represented as a square with multiple arrows facing in different directions. My habit is usually 2 arrows in opposite directions, but you might see more than 2 arrows, but I can guarantee you those arrows will always be facing in different directions to each other. Physically, switches usually look like this, with lots of RJ45 Ethernet connectors for us to plug into. And switches are quite cool. They operate primarily at OSI layer 2. Although you do get some switches that can work at OSI layer 3, that's a conversation we'll save for later on in your journey. More importantly is to understand the logic that all switches have when forwarding stuff. Switches make forwarding decisions. They are intelligent devices, and they make those forwarding decisions based on MAC addresses. What they'll usually do is they'll read the source MAC address in the traffic. At OSI layer 2, we usually call the traffic a frame, but if you hear people calling a packet, forgive them. They're making mistakes. And if you do it as well, don't feel bad. I do it too. You have the switch reading the source MAC address in the traffic and then associating that MAC address with the interface number it saw that traffic arrive on. That association is kept in something called the MAC address table. This will allow the switch to remember that MAC address for the future, so that if anybody wants to talk to that MAC address, it knows, I need to send it out of interface number 3 or interface number 12 or whatever interface ID number the switch uses. Then the switch will look at the destination MAC address in the traffic and go and see if it has that MAC address in its MAC address table. If the switch does find that MAC address in its table, it will send the traffic out of the associated interface only, so that it doesn't waste anyone else's time. But if the switch doesn't find it, the switch will then send that traffic out of all interfaces and potentially waste a lot of people's time. But the switch is doing it to maximize the odds that the traffic does get to the recipient. And hopefully the recipient replies. And then the switch will be able to learn their MAC address when the reply comes through, so that it can only send it out of that one interface in the future. So switches are pretty awesome that way. But we have a little bit of interesting variation with our switches. You get unmanaged switches and managed switches. With unmanaged switches, there's no configuration capabilities whatsoever. You cable them up, both with power and network cables, and it just performs its ordinary switching operation that I just described to you. But in the enterprise environment, you might be using managed switches, which can be configured to perform various tasks. Obviously, it performs its switching operation, but it can do other things that do traffic management, traffic inspection, and some network security capabilities, which, as you can imagine, in a larger enterprise environment would probably be very desirable. Your unmanaged switches, though, generally cost a lot less because obviously they're doing less. Whereas your managed switches, you pay a bit more for them. Unmanaged switches are easier to implement because, well, cable it up and it does its thing. Whereas managed switches can be more complex to implement if you are trying to take advantage of their better capabilities. The good news, though, is that you don't have to set up all of those features. If you just cable up a managed switch, usually it does the same thing an unmanaged switch will do, make switching decisions. But if you don't take advantage of those features and capabilities, you've spent a lot of money for what exactly? The frustrating thing is, though, you can't easily tell the two apart. On the left here is an enterprise unmanaged switch, and on the right side here we've got a managed switch, also for enterprise networking. The only thing that'll give it away to you is if you look closely at the interfaces. There'll usually be one interface, often apart from the others, and it'll probably be labeled console or con0 or something like that. That is the interface that an administrator will plug a special cable into, called a rollover cable, and then do some initial setup through the command line. Now, the initial setup will usually be just to get enough up and running so that the administrator can do the rest remotely, because believe you me, standing in a data center is not fun when you have to do config. So you get as little done in the data center as possible, just enough so that you can do the rest remotely from your comfortable office chair, preferably with a cup of coffee next to you. And then, Power over Ethernet, a very interesting technology that's been introduced over the last couple decades. So the whole idea of Power over Ethernet is that we are going to deliver power through a network cable. And the power will be done either by a switch or a PoE injector. So if you're looking at doing it by a switch, you've got to obviously check that the switch you're buying does Power over Ethernet. If it doesn't, you can get a PoE injector. And what you would do is you run a cable from the switch to the PoE injector, and then another cable from the PoE injector to the appliance you want to deliver power to. Now, in terms of power delivery, it is DC power being delivered to a device via an Ethernet cable, not AC power, DC power. So it'll be powering up things like voice over IP phones, wireless access points, IP cameras, and other such similar things. Sadly, we are not able to use Power over Ethernet to charge laptops or anything like that. Personally, I think that was a wasted opportunity, but hey, I don't get to decide how the world works. Now, the big advantage to this is, especially with things like wireless access points and IP cameras, if you need to install a wireless access point or a camera somewhere and it does not have a power plug nearby, you can either get an electrician to come and install one, which will possibly cost a lot of money, or you can run a data cable there, which you can do yourself. No special license or permission required, really. And the Power over Ethernet is able to deliver enough DC wattage that those devices can run without too much difficulty. Now, in terms of the wattages available, we've got about 3 PoE standards at the moment that you need to worry about. Now, if you're looking at those codes and panicking, please don't. You're going to see IEEE 802 a lot in networking. So the IEEE, or the Institute of Electrical and Electronic Engineers, is a standards body for a lot of networking and physical communication standards. And they define a lot more than just networking. But if you ever see 802, that is an IEEE networking standard. All of their networking standards always begin with 802. It's based on the month and the year the IEEE released their first networking standard, February of 1980. So just treat 802 as network and then worry about what comes after the dot. Usually you'll have a number and some letters that come after the dot. The number is indicating the type of network. For example, .3 is the Ethernet standard. .11 is the Wi-Fi or wireless LAN standard. And you'll learn more as you go along. The letters that come after the numbers are there to represent amendments or improvements to the original standard. Usually we start out with one letter, and obviously when we work through A through to Z, we then go over to using 2 letters. So the first PoE standard is 802.3AF, often known as PoE. And that can deliver at most 13 watts of DC power. Then we have 802.3AT, commonly known as PoE+, which can deliver up to 25 watts power max. And then you've got 802.3BT, commonly known as PoE++, which can deliver up to 73 watts of power. Now, depending on the appliance you want to power, you obviously want to check what the client side or powered device needs from a wattage perspective or a PoE standard perspective, and ensure that the switch or injector you're planning to use is able to sustain that power delivery. We also suggest that you try and use at least a Cat5e cable for PoE and Cat6 or higher for PoE Plus and PoE++. In a later video, we will talk about the Ethernet cable standards you do get. But for now, that is a suitable introduction to networking. And if networking sounds interesting to you, believe you me, you can make an entire career out of network support and administration. Now, I hope you found that video helpful and interesting, and I'd like to say thank you for watching it. I really do appreciate it. If you're enjoying this content, please don't be afraid to subscribe and like it. And if you have any friends or family members, colleagues, peers, or co-workers who would be interested in learning this kind of stuff, don't be afraid to share this video with them. Otherwise, though, I'll catch you in the next video.